Okay, welcome back to System Software. So we are right in the middle of learning about processes and how we can use the system call API that Unix-like systems give us to manage processes and also manage their I/O. Last time we looked at process creation, did some homework on that. And also keep in mind the file system project, we're about halfway through, but we do, what's that? Little under 2 weeks, about a week and a half. So questions about last time, questions about the project, logistics questions. Yeah. The what? Yeah, it's in C. It's in C. Yeah, I don't know. Sorry if that wasn't clear, but yes, FS project is in C. All right, let's go over the other questions. Let's go over the homework from last time. Uh-oh, no internet. I'm gonna open up the homework without it, although I won't be able to take attendance. Okay, so here's homework 10. First question is, what is a process? It's getting a little repetitive, right? So what's a process? I actually couldn't understand it of you, but I'm pretty sure you said running program. Yeah, that's right. So which system call creates a new process? Fork. Yeah, good. So when fork is called and you duplicate a parent process, are all open files copied or just the standard I/O? All. Good, yeah. All open files are copied. When a new process is created, how can a program determine whether it's the parent or the child? Or well, it's like, what's one way that we saw? What's that? PID could be one way, although how do you know which PID is the parent, which PID is the child? Yeah. When you fork, the child process returns 0. The parent process returns a positive number, which is the process ID of the child. What system call changes the program that a process is running? Exec, yeah. And then what does exec return if that system call is successful? That's kind of a trick question. It doesn't return at all. Technically it returns nothing, but doesn't return at all. All right, questions on any of those questions? Anything from last time? Okay. All right, that was pretty quick. Any other questions? FS project, code stuff from last time? All right, let's take attendance. Okay, so today we're going to look at redirection. So recall what redirection looked like in Bash. So does anyone want to give me a refresher? What happens? What is redirection in Bash? What does it do? Yeah.
Doesn't it pass the input? Doesn't redirection change where the input or output is coming from?
Yeah, that's exactly right. Yeah. And so before it's changed, where does the input or output go by convention for like core Unix utilities? Yeah. Standard in, standard out, standard error. Now redirection isn't restricted to those, but the techniques we saw in Bash before was that we could just use this really simple syntax, this little angle bracket, which kind of looks like an arrow, to tell Bash that we want to run this program, but we'd like to have its output stored in this file instead of whatever standard out is. So if I run this command, what's going to happen? Where's my I/O going to go? Yeah.
It's going to store the result in outfile.txt.
It's going to store whatever the output of cat is into output.txt. So what does cat do? Yeah, that's where the name comes from. Yeah, it just basically, yeah, copies standard in to standard out. It writes, if we run it the way we run it here, copy standard in to standard out, yeah.
If you run just cat with no parameters, will it print the entire directory's worth of contents to the terminal?
That's a good question. If you run cat without any arguments, where does the input come from? Well, it comes from standard in, and yeah, if you're running in bash, then it's going to be the terminal as the input. So what's going to happen when I run cat from the terminal? It's going to print out what you type. If I don't type anything, it's going to block waiting for input from standard in. That file's still open. Bash has set the terminal to be the input to this utility. And now it's just, that's why it looks like it's hanging, but it's really just waiting for input. It's calling read. This is the read syscall, and it's waiting for input. Once I have input, it takes that and it just writes it to whatever standard out is. Standard in and standard out are both my terminal, so whatever I type in gets echoed to the output. That's why if I redirect the output, say file cat.out, again, I haven't redirected standard in, so it's still coming from the terminal. Control D is how you can close a file if you're reading from the standard in. And now if I have this new file, cat.out, that was created by bash in order to redirect the standard out. And what should be the contents of that file? Whatever I wrote here, right? Whatever I wrote here, that was being echoed to standard out. Because I redirected standard out to this file, that file will now contain whatever I had put into standard in into cat. So cat's like an identity function, or like a simple example of I/O, because it's just, yeah, copies standard in to standard out. Here's a more subtle one. What about the echo command? Does anyone remember what the echo command does? What's that? Print what to console? Okay, that's an interesting question. So if I type echo and hit enter, what happened? What was printed out? Nothing. Is my terminal hanging waiting for input to echo? No, because echo doesn't print, or doesn't read from standard in. Let's see if it says what it does here. Echo the strings to standard out. It doesn't take the standard in, it takes the command line arguments. So it's similar to cat in that it just copies something to the standard out, but it takes whatever the command line arguments are, which in this case are hello, comma, and world, and it prints those to standard out. So if I redirect this to a file called echo.out, what should I see on my terminal? Nothing, right? Nothing, because I've redirected the standard out. And I've got this new file created, echo.out. And what should be in there? Well, whatever I'd put on the command line for echo. So echo takes arguments, puts them to standard out. Cat takes standard in and puts them to standard out. Okay, and then, in bash, we can use these two angle brackets to change standard in or standard out to a file instead of whatever standard in or standard out were. Okay, questions on redirection in bash? So a more subtle question is, why is standard out or standard I/O relevant here? So I mean, this is sort of an abstract question, but the point is that cat and grep and echo, they were programmed to use standard out. So the programmer for those tools just used printf, or they used the standard out file and the standard in file. And the reason they wrote it like that is because they know that there's this Unix convention that all programs are given standard I/O, and that other tools like bash or other parts of the system that want to run those programs can just redirect standard I/O to change the I/O of those programs without having to actually reprogram those tools. So that's the benefit of using standard I/O. Okay, questions on that concept? Okay, so in this lecture, we're going to look at is how bash actually implements this using Unix system calls. So the Unix API provides some support for being able to do this kind of redirection. So the whole notion of having standard I/O is this Unix concept, and then we're going to see how that bash actually implements this redirection feature using syscalls and just the standard file I/O APIs. So remember the kind of three main things we have for file I/O: open, read, and write. There's also close. There's other operations as well, but these are the ones we went over last week. And unlike the C library standard where you read and write to those file types, so you had like fopen. Fopen, it's in section 3, that's the library standard. These return a file, and like printf or fprintf, which is like, kind of like one of the tools that will write to a file system. This takes one of those file objects. But open is different. Open returns just an integer. What was that integer? What is the return value of open? A file descriptor. So if you look at chapter 5 of the Linux Programming Interface textbook, we talked about this a little bit, so we talked about process creation. But file descriptors are a pretty simple idea. The kernel or the operating system just keeps a table listing all of the open files you have in your system. So over here, this is your file system. These are the inodes that actually store the data on disk or some storage medium. And your process just has a giant array that effectively points this index 0 or index 1, index 2, points to a table in the kernel, a system-wide table that keeps track of all files that are open by any process. And those open files are then have a pointer to the actual data on disk. So if I copy process A to process B, this table is just being copied. So it's a copy. They're like pointers. They're pointers. So we're just copying a pointer to the open file, and that open file is pointing to the actual data. So when you fork a process, it's this table that's copied. The data on disk stays the same. That's unaffected by it. It's just a pointer to the open file rather than the actual file in any way. So that file descriptor is what gets returned by open, and then, as we saw last week, that's what you pass to read and write. That's what you pass to read and write in order to tell the system which open file you'd like to write to. And then it's the system's job to figure out what's backing that. It could be the actual storage medium, it could be an inode number, or it could be an Ethernet card, it could be a USB drive, it could be a serial port. But that's up to the system. The system is going to do that. So as long as you have a way to get a file descriptor and open a file, then you can read and write to whatever I/O device you'd like that the system supports. Okay, so that's file descriptors and kind of quick refresher of file I/O. Questions on that? Questions on those? We did a bunch of exercises in class where we programmed using the kernel level syscalls for file I/O. Okay, so let's take a look at an example of writing to standard out. So typically, how do you write to standard out? Or how have you been taught to write to standard out? Just printf, right? Printf. So let's look at the way we would do this using the syscalls, using the write syscalls. Let me actually switch to here. All right, here's an example of a program that just writes to standard out. So I've got a string here that I want to print out. I've got the size of it. And here's my call to write. So remember what the API is. It takes a file descriptor, it takes some buffer, some byte buffer, and it takes a count of bytes you'd like to print out. So here, For the file descriptor, I just give it this macro that's defined to be whatever the file descriptor for standard out is. So let's see this actually working to hopefully convince you that this actually does what it says it's supposed to do. So here we go. We've got hello world being printed to the terminal. And as we know, Bash creates this process, gives it standard IO, gives it standard in, standard out, and standard error. And with no other redirection or nothing else, Bash will just use whatever Bash's standard IO is, which is the terminal. Questions on that so far? Questions on that?
Could you explain again? So right now, what's being is the value being like is right equal to -1 or no?
Oh, okay. So why are we checking whether right is -1? Why does this code do that? So remember, for all syscalls, you got to do your own error checking. So that check for -1 is just seeing whether right returned an error. That's all that's doing. So the return value, see here, the return value is just the number of bytes written, or -1. That's the return value of right. So this is, a little different from printf, which I think does actually return an integer. I think it also might be the number. Actually, I don't remember what it returns. Oh yeah, it returns the number of bytes. So printf also does this, returns the number of bytes. And actually it does return a negative value as well. But just to show you the practice of using syscalls, I'm just showing you the error checking.
So just to make sure I understand, -1 isn't what's right. Like, so it's saying if -1 is equal to right, but your output is not that right. Like,
Yeah, the right returned something other than -1 when I ran it this time. But if there were an error with the kernel, if the kernel returned an error, it would execute this code.
Yeah, so the reason I was asking is because if it did equal -1, I want to know what the std_out_file would be.
std out file number, this is the file descriptor for standard out. So you can separate this from the error checking. The error checking is not really what I'm trying to show here. So maybe you're just having trouble with the syntax of this. So this is just, in C, you're allowed to call functions in conditions. These conditions are they're just expressions. So you can call them in there, bless you. So this is identical behavior. This code will behave identically. Other questions on this? So this is just the write syscall we saw before for writing to files, except here we're writing to standard out. So this is a macro that's defined in the Unix standard that gives what the file descriptor is. Now the file descriptor is an integer, so this is going to be backed by some integer, but this is how you access the standard out file descriptors. Yeah?
For the exams, are we expected to memorize all this?
No, I'm not going to expect you to memorize exactly this stuff. You have notes, pages of notes, so you can use that if you want to have reference material. But if you I don't think I would remember this exactly all the time. If you said standard out, no, or number or something, that would be fine. Okay, so a question here. When we saw, oh yeah, sorry, go ahead.
Why do we use this and not printf?
So printf uses this. So if you remember from our lecture, this is how printf writes to standard out. So printf is just a library code that sits above the system and ultimately calls it. So in this class, I'm showing you the low-level stuff, so you can see how the system software is actually implemented. And also, when we do these low-level system stuff, we can do things that may not be provided for you in the library. But yeah, typically, if you're doing writing to the console in your system, you probably want to use printf. Now, if you're doing, say, network programming, or other sorts of I/O that's not just to something that C library supports, like buffered output, then you will actually use this kind of stuff. So if anybody does any embedded work or network programming, you will likely use the low-level write calls. Especially embedded systems may not even have the C library. You might just like only have this. But yeah, so printf under the hood, I think I showed it somewhere last week where a piece of the implementation of printf where you see the call, I think the call to write, and you see the hard coding of standard out there. So the printf equivalent of this will be something like fprintf standard out, ... or just, yeah, I can just say message one here. Has anyone actually used the standard out file in printf? No one's ever used this? Anyone ever used standard error? Use this? Okay, yeah, use this. So what's the difference between standard error, standard out, and these? You can see this is section 3, this is the library functions, and you can see that this has type file. This is the library type. So this is a wrapper, effectively a wrapper around file descriptors. Whereas, actually I don't even know if there's documentation for this in here. Yeah, there's no entry for that, but I have the specification here. Down here somewhere. Oh yeah, here. So this is in a header file called Unix standard. So here's the definitions of those. And I don't know if there's any other systems that don't do this, but I think by convention, the first 3 file descriptors, 0, 1, and 2, correspond to in, out, and error. But just, I guess in case that changes, or to avoid magic numbers, you can use these macros instead. So this is where they're defined. They're literally just constant numbers. Because remember, all the file descriptor is just an array, an entry, an index into this array of file descriptors. So when you say 0, you're telling the kernel, hey, look up open file 0 for this process, and use whatever file is backing that to do your I/O, to write out to. Okay, other questions on this example? Yeah?
Just replace that first parameter with 1, and it'll be equivalent.
And it would be what? It would be equivalent, yeah, that's right. So this would be equivalent. This would be equivalent. You could replace it with 2, and where would that write to on this system? Standard error, yeah. So it would also go to the terminal, but if we redirected standard out, this would still be written to the terminal because they're 2 different files. So this is standard error. All right, other questions on this example? So it's just the same file operations we saw last time, except we have this standard out. We're actually using standard out. All right. Previously, when we did file I/O, we opened a file. So why is there no open here in this example? How is it that we were able to write to the console, but we didn't have to open any files? We're writing to a file, right? And it printed to the console. We actually got the output, the write succeeded. But we didn't open any file. We just wrote to this file descriptor, and it worked. We actually got some output. Why didn't we have to call open? Yeah.
Because it's automatically open for it.
Yeah, it's open for you. So the system, in this case bash, when it creates the process, it opens those files on your behalf. That's like why standard I/O works. Because this program, we as the programmers, we don't have to worry about where these standard I/O comes from or goes to. We don't have to worry about what hardware or file is backing this. We can just start writing a program and start immediately using I/O. And if for whatever reason we want to change this from a file or to a different file, or to go over an Ethernet socket or to go somewhere else, we don't have to redirect any of that ourselves. We can just always write to standard I/O, because whatever program is invoking it is supposed to open those files for us. And that's why bash redirection works, because I can redirect ls to a file, and I don't have to reprogram ls. ls just effectively does this. They probably do printf, but they do this. They write to standard out. And because of that, bash can decide whatever that I/O is going to be before it runs ls. Questions on that? I know it's like a really subtle point, but it was it's kind of a lasting design decision from the Unix developers about I/O. Questions on this? Okay, so let's take a look at how we can actually redirect these. Let me get back to where I was. So that's writing to standard out. So there's another system call, a Unix system call called dupe for duplicate. And let's take a look at the man page for this. So dupe takes a single file descriptor, and what it does is it creates a new file descriptor that refers to the same open file. So remember, this is duplicating the file descriptor, not the file. So if we go back to our table, all it does is it takes whatever entry you give it. So let's say you give it file descriptor 2, and the next available file descriptor is 20. It's literally just going to copy this pointer here. So now both these file descriptors are going to point to the same file. So it's like copying a pointer. So now we have 2 pointers to the same open file. That's what dupe does. Yeah.
Sorry, just to clarify, does it point to the file or does it point to the file's pointer?
It points to, think of the file descriptor as a pointer to the file, ultimately. So the file descriptor is an entry in an open file table, or a pointer to that open file table. So don't worry too much about the system part here. Just remember that the file descriptor is not a pointer to the data. It doesn't reference immediately the data in the file. It's a pointer. So this open file table has a pointer to, ultimately, the actual file backing it. So if I copy that pointer, I now have 2 pointers. So here you can see these are 2 different processes, but this file descriptor 2 in this process points to the same open file as this process's file descriptor. But I could have 2 file descriptors in the same process also pointing to the same open file. Yeah.
Could you theoretically have, could you have as many pointers pointing to the same?
Yeah. Yeah, you could have as many pointers as you like. So let me show an example of dupe, just to give you an intuition about what this does. So here's code. I already have the code up here. Okay, so let me walk through this program. So the very beginning of it is identical to what we just saw. It takes a string and it writes it to whatever the standard IO, whatever standard out is. So standard out is always, on this system, is always file descriptor 1. So this just writes to file descriptor 1. Next thing we do is we call dupe. So we take standard out's file descriptor, we call dupe, and we get this new file descriptor. And then we write a different message to dupe FD. So we've taken standard out, we've called dupe on it to get a new file descriptor, and then we've written goodbye to that file descriptor. So just like intuitively, what do you expect? So if I run the program like this, what do you expect to see on the terminal when I run this? Knowing that when bash invokes this program, it's going to make standard out to be the terminal. What should we see on the command line when we run this program? So we've written here to standard out, then we've duplicated the standard out file to a new file descriptor, dupe FD, and then we've written to that duplicated file descriptor. What should we see in our output? So who says goodbye? We should see goodbye. Anything else printed out? Just goodbye? Let's take, or both? Okay, so it's either both or goodbye. Who says both? Gonna be printed out. Who says just goodbye? Who's just like totally confused? Totally confused. Okay, a couple people. Okay, so I put a little sleep in here so we could wait. So we've got hello world. This is because identical to what we just had before. We've just written to standard out. Just like when you call printf, this is printing out this message, hello world, to standard out. And now this code here, we're writing to a different file descriptor. We're writing to a different open file. But we got that open file by duplicating an existing open file, so it's backed by the same output device. And we wrote to that open file descriptor. So just to kind of show you, convince you that these file descriptors are different, I'll use printf for this. Let's do it this way. Whoops. So here we can see what the actual file descriptor number is. And yeah, so this file descriptor is 1, as we expect. We saw the define for it. The dupe file descriptor is 3, but yet they're still printing to the same place because I've simply taken whatever entry was here and copied that pointer to another open file here to FD file descriptor 3. And so if FD1 was pointing to this open file 23, so this is system-wide, so it's just keeping track of every process's open file. If that FD1, file descriptor 1, standard out, is pointing to this open file, 23, and I just copy that 23 to file descriptor 3, they're going to be pointing to the same open file. So if I write to both of those file descriptors, they're all both going to go to the same output. Questions on that? Yeah.
So what does 1 and 3 represent?
Sorry, second. Sorry.
So what are 1 and 3 represent? Are they just random numbers?
They're just entries into this. There is a table that just keeps track of all open files that you have in your process. It's per process. So file descriptor 3 may differ in which file is backing it in different processes. But when you call fork, when you make a new process, part of the state of that process is which files have been opened already. And this is just a table that keeps track of all files you've opened. And so I think that the typical implementation is just start at 0, and then bash or whatever invoked you will open up 0, 1, and 2 for you. And then whenever you call open, a new entry is created in that table. So here 20 files have been opened. If I call open again and there's no free file descriptors, a new entry will be created in this table and you'll get file descriptor 21. If you close a file like file descriptor 3, typical implementations will just take the next lowest file descriptor, whatever's free in the table. But it's just a record. It's just a logbook of which files you opened, and they're given numbers, and you can use, that number is what you pass around to represent the open file for when you want to call read and write. Does that make sense? Yeah.
Is there a specific order for numbers? Like, is it first one opens, the first one that gets the number?
It's like a simple, very simple C implementation. So it's just an array. So if you want to add an element to array, easiest thing, you just put it at the end. It's like think of it like a dynamically sized array, and they'll do some a garbage collection. So if you close a file descriptor, it'll keep track of the next free one. I mean, you can imagine really simple C implementations of this, right? You just start with some fixed array memory size, and then you keep track of the end of the list, right? So when you add 0, 1, and 2, you say, okay, the next one is 3. Then when you add a new one, you just use that and then increment. If you run out of space, you double the size. If any of are freed, you just loop through the list and see which ones are free. So this is kind of one of the beauties of Unix, is that at its core, some of the implementations are like fairly simple. I mean, I'm not saying it's like easy, but the ways to implement it are fairly simplistic. And these implementation details are kind of exposed to you a little bit. The fact that the file descriptor is just an array index into the open file table. There's no fancy, like open file objects or anything. It's just a very kind of raw, low-level exposure to how the kernel implements the process, how it implements the state of the process. So it's just an index into this table, this open process or open file table. Other questions on this? So you can see, even if you don't take operating systems, this opens you up to understanding a little bit how the actual underlying operating system that virtually every computing device relies on these days, especially Unix-like systems. Yeah. I can't see. Oh, over there. Okay, sorry. Yeah.
So is this kind of just like function, kind of like an append function like Java or something?
Yeah. I mean, under the hood, what append does, if it's backed by an array, is something like this. Yeah, I mean, you could imagine implementing it something like that. And it's a little different because you can close things in the array and free space. It's kind of like malloc, what malloc does. But yeah, this is just, I mean, hopefully you learned about this in CS1. How do you implement a list using an array as the backing? And this is kind of the same idea, very similar idea. All right, other questions on this? So all dupe does is it just takes some existing open file and just copies it to another open file. Okay, so here's another example. If you, I'll leave this as an optional exercise if you want to play with some other examples. Oh yeah, so this one I'm opening a file and then duplicating it. But same idea. I already have the open file, so I won't show that one. Okay, so why have this syscall? It seems almost so simplistic to be like useless. Why would you bother doing this? So why would you want to be able to duplicate file descriptors? Yeah.
Maybe so more than one thing can access it at a time.
Say again?
More than one thing can access it at a time.
Well, more than one thing can still already access it. So you could write the program, or you could have multiple programs accessing the same file. Because this is system-wide, the open file table is system-wide. Two processes can still point to the same open file. But why within a process would we want to, or why bother being able to do this? A hint is that it's like the name of the lecture. Redirection, yeah. So you can use this. So I showed you an example where we're copying standard out. But we could do this the other way. We could take an open file and then use dupe to replace one of the standard I/O file descriptors. And voila, we've got redirection. All redirection is just changing what standard I/O points to. Standard I/O is literally just the first three entries in this table. So if we have an operation that allows us to replace or change what these open file descriptors are, then voila, we've got redirection with very, very simple mechanics. Okay, so I didn't tell you completely about this. I hinted at it, but you can close these file descriptors. And when you call dupe will use whatever the lowest file descriptor available is. So this, I don't know, did anyone read that worse is better essay? Did anyone find that? Maybe not, but if you can't find it, or let me know on EdStem, I'll send it to you. But one of the kind of beauties or staying power of Unix is that the implementation, compared to, I guess, systems at the time, was pretty simplistic. So the API kind of exposed to you some of the internals of how the system was written. And so the fact that it uses, so it says here, the new file descriptor is guaranteed to be the lowest numbered file descriptor that was unused. And the reason that I think it's designed like this is for a redirection. So if I close file descriptor 1, well, now file descriptor 1 is the lowest file descriptor available. So if I call dupe, that's the one that's going to be used for this. So you can do this kind of fancy redirection with pretty simplistic mechanics, as long as you have a really well-defined behavior here. That kind of like very low-level C-like array management behavior is exploited to be able to do redirection, this kind of high-level, powerful technique. This is kind of the story of all systems. It's low-level stuff is used to make high-level abstractions. Like tumblers in a lock are used to make the notion of a locked door. Okay, so for redirection, dupe is a little bit more onerous to use because you have to first close the right file descriptor and then open a new one. So there's a variant of this that combines these two steps. So dupe 2 will replace an existing file descriptor for you. So dupe 2 performs the same task as dupe, but instead of the lowest number, it uses whatever file descriptor you gave it. So dupe 2 has two parameters. Your old file descriptor, which is, it's a little confusing. The old and new is a little confusing. I made this mistake when I was writing it, but I'll show you the example and it'll hopefully become clear. So old file descriptor is an existing already open file, and new file descriptor is the one you want to overwrite. So if we want to do redirection to say standard out, new file descriptor would be standard out. So if we're trying to change where standard out goes, we take some existing open file and then we replace standard out with it. Questions on that concept? So it just allows us to specify two of these file descriptors, and we can say explicitly, take file descriptor 20 and replace file descriptor 1 with whatever that open file is. And that's redirection. So you really just have one call, and you can take advantage of this powerful systems technique of changing the I/O of a program without doing any changes to that program.
Can you show an example?
Yes, I can, and I will. Yeah, okay, so here's, this, I'll just show the example. Here's the example. Okay. All right, so this setup is really, really similar to the dupe example we just saw, where we wrote to standard out, duplicated standard out, and then wrote to that duplicated file descriptor. It's a slight variation here. Here, instead of duplicating standard out, we're going to open a file. We're going to open this new file. It's called just like new file, redirect standard out. We're going to open it just like we did before. And then here's our dupe command. We're going to take that newly opened file. Remember, new file redirect. This is given a new file descriptor, FD. And we're going to call dupe2 to effectively overwrite what standard out used to be. So when bash started, standard out was the terminal, and this single system call is going to take whatever my open file was, my new file redirect, and it's going to close and reopen, so it's going to blow away standard out. This is the redirect syscall. And so just to illustrate this working, I first write to standard out here before I do the redirection. I open a new file and do the redirection, and then I just write to standard out again. So notice, in both cases, we're writing to standard out. But what will be the output of this command when I run it? So when I run it, so first, what will we see on the terminal? Give me a second to kind of digest this a little bit, work through it. What should we see? This is a little big. What should we see on the terminal, firstly? You can call it out or raise your hand. Right to original standard out. So we should definitely see this, right? We just saw an example of almost this basically this identical program with different text. So this should go to the standard out. What about this write? So we're also writing to standard out here. Will this show up on the terminal? So here, this is after we've done the duplication. We've opened a new file. We've blown away the existing standard out file descriptor with a newly opened files file descriptor. And now we're writing to standard out. Will that go to the terminal? What's that? No, it shouldn't go to the terminal. We should go to the new file, right? It should be redirected to the new file. And then a last little trick question here. Here's printf. Where will that go? Okay, who says terminal? Who says file? Okay, let's see where it goes. Okay, we only saw write to standard out here, right? We didn't see redirected or printf. So redirected, the reason it goes there is because we duplicated. We used dupe2 to overwrite what the previous standard out was, which is the terminal. We've changed it to be this newly opened file. But what's kind of subtle and clever about this is that printf under the hood is really just calling this. This is all printf does under the hood. It calls write standard out. And this is the beauty of redirection and standard I/O, is that without changing any code, you can write a program that just uses printf everywhere and scanf. And without doing any extra work, you are now open to literally any I/O device. It doesn't even just have to be file system. It can be USB, it can be serial ports. You can take a little Arduino microcontroller, I think that uses C, or Raspberry Pi. And as long as there's drivers in the kernel for whatever that I/O device is, maybe it's an LED, maybe it's a USB drive, you can just use the same I/O to write to all of those devices. So we've, under the hood, swapped out where this output goes. We've swapped out what the I/O is for this program. And so then whenever we use any of the tools that give I/O to standard out, all of that will be redirected to that new device or new file. Questions on this? I know it's a subtle thing, and it's a lot of C code. It's a subtle thing. Questions? Yeah.
How would you redirect it to go back to the terminal?
Oh, that's a good question. So at this point, that's going to be really hard to do because we've lost this file descriptor. It's been closed. So what could we do? That's kind of a good question. Let's do this as an exercise. So how could we still retain? What could we do to retain being able to output? So let's say I want to write to the terminal again. This definitely won't work, right? Because we've already redirected standard out. So how can we write to the terminal again? Yeah.
Could you fork it and then just have it be the same program that replaces it?
Okay, you could fork it. Yeah, you could fork it. Do we have let's say within the same process. Do we have a tool or a system call that will allow us to copy a file descriptor? We do, right? We have dupe. So we could just use dupe, and I'm not going to do I should probably do the error handling. So I'll just get a new file descriptor for what standard out used to be, whatever file was backing it. Just use dupe, just what we saw before. So I'm going to copy a pointer to that open file, and you're supposed to do proper error handling here. Let me make sure I do that. So I've just duplicated what standard out was before to a new file descriptor. And now I should be able to how long is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, I think. If I count the null character. Let's see if this actually works. Let's see if I broke something. I broke something. Oh, I forgot to actually declare the type of it. So they're just integers. Remember, they're just indices into a table. And let's see if this actually works. So there it is. It's still, I didn't do a new line character. I probably should have done that, but here we go. So we've still written to our file. Oh, so I didn't even show our file yet, but still written to my file. But because I copied standard out to a new file descriptor before I closed it with dupe 2, now I still have that file open. I can still write to it, that terminal file. So that was an interesting question. But yeah, we have that. It's, one use. This is one use of being able of this file system. So yeah, if we wanted to write a program that swapped between original standard out or standard I/O and some file or some other device, this is what we could do. Okay, questions on this? Let's take a look at this new file. So as we talked about before, here's the output to the new standard out, which is this file called new file redirect standard out.txt. And just as we reasoned before, because printf really just calls write standard out under the hood, doesn't care what standard out is, as long as it's an open file, it'll write to it. It'll write to that file because we've replaced, with dupe 2, we've replaced what file is backing standard out. So this is kind of the same level of like thinking about pointers. So the file descriptors are just like pointers. So in the same way, if when you copy a pointer, you're not copying the data behind it, right? You're just copying the pointer. So in the same way here, if we replace standard out, we're not changing the terminal in any way. We're just changing what's being pointed to by it. And in the same way, we can copy the original standard out data to some other pointer and still retain the ability to print to the terminal. Questions on this? So you can kind of see, like pointers, most application languages, you don't really have to deal with pointers anymore, like Java and stuff. But low-level systems programming, pointers are like kind of an important part of doing this low-level systems stuff. Questions on this example? So you have code here, and this will work on Eustace or your Unix system. You can like play with it yourself, get comfortable with it. But it's, important to know this in order to see how Bash gets a little more complicated. There's a lot more steps when we have to actually implement this in Bash. But this is the basics of basically I/O management in Unix. Okay. Let me do a diagram just to hopefully make this clear. So Bash forks my program, my redirect program. And when redirect is created, so Bash has standard IO here, standard out. This is to my terminal. So when Bash forks this process and it executes my program, my standard out is also pointing to the terminal. When I call dupe2, what it's doing is it's replacing this standard out with a new open file, my new file that I've opened. That's what dupe2 is doing. It's replacing standard out, or that call to dupe2, to that new file. Questions on that? Does that kind of make sense? So just kind of abstractly what dupe2 is doing in this case. Okay, so you can also do this with standard in. I have an example here. You can try it on your own. Okay, so this is where we start combining syscalls to see how Bash is implementing this, kind of the power of combining these various system calls. So here, we're going to do what Bash does. We're going to use this redirection, but we're going to do it for a different program. We're not going to do it for our own program. We're going to do it on behalf of another program. So in this case, I think I use ls. I can't read this code here, but I have the example here. Oh, here, okay, so I don't run a program, I just make a new process. So here, we're just gonna see the first step. Making a new process, you run fork. So here, we're gonna fork the program, and then for one process, we're going to redirect standard out. The other process, we're gonna leave it the same. So this is exactly what Bash does. So this is our code from before for creating a new process called fork, right? In the parent, we're just gonna print the standard out. In the child, we're gonna call dupe2 to redirect standard out, and then call printf. So just quick pop quiz, this printf, where is it gonna write to? Is it gonna write to the terminal, or is it gonna write to somewhere else? So you can see here, it's right after this dupe2 where we overwrite standard out. It's gonna go somewhere else. So it's gonna go to whatever FD is. FD, I've just opened a file. So just like the previous example. So this is combining the previous redirection example with fork, where we make a new process and then redirect that child process's output. So let me walk through the code again. So path, we get it from an argument. We open, we call FD, and now we call fork. And remember, fork duplicates the whole process, including its memory state. So this FD, this file descriptor, the existing open files, that will be identical in both processes. But we do different things depending on whether we're the parent process or the child process. The parent process just calls printf. And so where will this be printed out? Do you think it'll be the terminal or to some other place for the parent? So the parent, there's no dupe2 call for the parent. Terminal, yeah, so it stays in the terminal, standard out. But in the child, it's a different process, but it has all the same data, has all the same memory state. We do call dupe2 and redirect that standard output to a file. So let me show the example just so you can see it working, and then let's do questions. Okay, so as we predicted, we call child. There should be two processes being created, as we talked about last time, or one process being created, and the parent will still exist. In the child, we'll call dupe2 to redirect standard out to a file, this file that we created up here. and then parent will just print to the output. So here we see printf in the parent process printing to standard out, but we don't see child process being printed out. Why is that? Where is that data being output? To child file, yeah. And so here we see the output of printf to child file. So there were two processes here. The child process we called dupe2 to redirect standard out. The parent, we didn't do that, so that's why we see the output going into two different places. Questions on this example? So kind of have to wrap your head around fork and redirect here. Let me make a diagram for this one as well. Quick diagram. So I have this program called child. It was invoked by bash, so its output starts as the terminal. When I call fork, I get a new process. I get a copy of the child program, the child process running. So these are going to have two different PIDs. After I call fork, where does standard out, which file does standard out point to in this forked child? The terminal. It's the terminal because all open files are copied. So if the terminal was open in the parent before fork, the new process is going to have all the same open files, all the same memory state, all the same CPU state. And so both standard outs are pointing to the terminal. But when I call dupe2, dupe2 is going to overwrite standard out to whatever file I opened. But unlike the previous example where I called dupe2 on my own process, here I have two processes, and their standard outs are pointing to two different files. So when I called printf in the parent, it went to the terminal. When I called printf in the child, it went to this new file. Does that make it hopefully a little clearer? That kind of makes sense? Yeah. Oh, when I modified the previous example? Let me show a diagram of it. Let me show a diagram of that. Well, let me finish this section because I'm low on time, and then I'll show, if I have time, I'll show a diagram of that to make it clear. But it's just using dupe again to copy the terminal. So let me make a note to go back to this. Any other questions on this example? Okay, and so let me show the last example where we combine fork and exec. So if we use fork and exec together, what did we illustrate using that for? What did we use both fork and exec together for in process creation last time? Yeah. To create a what? We created a new process. We created a new process and also replaced the running program. So it's like when on bash you call ls, it creates a new running program. So it's a new process and a new program that's being run. So that example, to show the diagram of that, is we call fork on the program. That gives us a new copy of fork. And then when we call exec, that's going to replace, we call exec for the ls program. That's going to replace the running program of that process with ls. So that's fork and exec together. Kind of like that's what we showed last time. But in that example, we did nothing with I/O. So in this example, both standard out pointed to the terminal. But we can use redirection to both call a different program, one that we haven't written, may not even have the source code for, and change its I/O. So let me show a diagram of what that looks like first, and then I'll show you the code. So we start with a program called child, actually it's called child exec, and its standard out is the terminal. We call fork, that creates a new process running the exact same program with the exact same open files. To change the I/O of that child process, we use dupe2 to instead change its standard out to point to a different file, not the terminal. And then finally, we use exec to replace the running process with ls or some other program. And now we've done what bash does. We've been able to run a new program, redirecting its I/O for that new program. Questions on, conceptually, questions on this? All right, let's see the code for this. So this is child exec. Okay, so I'm just opening a new file. Here is the same template for fork, where we call fork, and then we've got a case for the child and a case for the parent. So here in the parent, we just print. That's going to go to standard out, the original standard out terminal, because we haven't redirected it. In the child, just like the last example, we call dupe to redirect the standard out of that child process, of the standard out of the child process to a new open file. And then this code, you may not remember from last time, but this is the exact code we use to change the running program, to run a different program in our process. So those are the three parts. Fork, two processes now. Redirect the child process using dupe, and then replace the running program with ls. Questions on the code? Questions on the code at all? Okay, so let's take a look at this program running. Okay, so what do we expect to be output from this program? What do we expect to see on the terminal for this program? Parent process. Anything else? The output of ls. Oops. I'll call it exec file. So it just prints out parent process. That's it. And what do we expect to see in exec file? Exactly, the output of ls. And there it is. So I print out exec file, and this is the output of ls. So I gave it the root as the thing as the argument to ls, which is why it's printing out the root. But yeah, and there's all the examples. Questions on this example? So it's bringing it all together. Fork, exec, dupe, all together for doing some simple tools for sophisticated process management. Yeah.
So if you ran your dupe before your exec, is it still going to print to where the exec has like?
If you ran dupe before.
Exec before dupe, is it going to like print before it redirects? Like, or does it work like instantly?
So the question is, if you ran exec before fork, right? Or before dupe. So if exec is successful, what does it return? It doesn't return, right? It just starts running the new program. So any code after exec, if exec is successful, will never be run. So that's why dupe is run first. This is the subtlety of this process management. That's why fork and exec are separate. Because fork creates a new process, and then you can do your I/O management or other manipulation of the process. Then you run exec in the new I/O environment that you created for it. Other questions on this code? All right, so let me quickly show the example I had before where I saved the process. I'll just show a diagram of it. So in that example, we didn't call fork. We had an existing process that pointed to term. We copied standard I/O to another file descriptor, and then we replaced standard out to another file here. And when we wrote to standard out, it went to the file, but when we wrote to this new copy terminal FD, it still wrote to the terminal. If that makes sense. So sorry for making that really fast. Ask when it's then come to office hours, and I can walk through that full example. You should have all the code, so take a look at it online, play with it, and see you next time.